So up to this point, we've been dealing with the conservation of energy without any losses. We're assuming that there's no friction and none of the energy is being taken away. So essentially, as this potential energy drops, the kinetic energy should increase. And if you watch the skater go down and back up, you can see the potential changing into kinetic and vice versa, the kinetic changing into potential. And the total energy is not changing at all. Okay? And we dealt with that and we calculated these energies with the following formula. That formula was kinetic energy initial plus potential energy initial equals final kinetic energy plus final potential energy, which just means that initial energy, the total initial energy, equals the total final energy. And if you look back at that simulation, the total energy is not changing throughout the whole thing. Uh, in the real world, this is not the case. And I will show you a demonstration of what that looks like now. And you can probably already guess what's going to happen. As I add friction to the system, we can see the total energy start to drop, thermal energy start to increase. Excuse me, the total energy is not dropping, but the kinetic and potential energy are dropping, and it's all being transferred into thermal energy. Okay, and that's all due to friction. You can see we're starting to lose energy into the thermal world. Everything's going into the transfer of heat due to the fact that friction is there. And we can start it over again. Let's pause this real quick. If we had no friction again, let's put them up. No friction, these kinetic and potential energies, he's going to get back to the same elevation. He or she, I think it's she, is going to get back to the same elevation every time. But add the friction, and that's not the case because we're starting to lose our potential and kinetic energy due to the friction that exists between the skateboard and the surface. Now, what does that look? What does that look like in a formula? Well, think about where what end you're losing the energy on, and that would be on the final end. You have that total initial energy over here. Uh, so in order to make this equation true, you need to add some kind of energy calculation that is related to uh, friction, and we use work. Specifically, we usually tend to call this work out. Okay, the work taken out of a system. Okay, so whatever your initial potential energy is, that's going to be equal to your final energies plus whatever you lost here. Whatever work you lost out here, work due to friction. Okay, and again, this is the force times the displacement or distance that this thing went. Force times distance. Well, we're specifically going to talk about losses due to the force of friction. Okay, and remember, friction is coefficient times force normal. Okay, uh, this is one way that you will see the formula written. Okay, if I rearrange my equation and I specifically want to know what the work out is going to be equal to, uh, I can do that. I can, rearrange this lettering, If you rearrange this lettering, here is what happens. You have workout subtracted to the other side. And in a few moments, you'll see why I'm taking workout to this side of the equation, to the left side of the equation, and moving my initials over to this other side. If you look, when I move the initial and potential, initial kinetic and initial potential over, I've got to subtract them over. So I'm left with, uh, you know, kinetic energy final minus kinetic energy initial. And if I think about what that is, and what potential energy final is minus potential energy initial, that is a change in kinetic energy. Remember, change is final minus initial, so delta, or change in kinetic energy, plus your change in potential energy, that will equal negative work out. Okay, this is another equation that you'll often see. Uh, that work is equal to your change in energy. Okay. Now we can also put work into a system, and we'll probably get into that a little later. But for now we're going to talk about work lost due to friction. But you can, change this up and put work into a system. Well, that work would be on this side. So you'd put the work in for the initial. You're initially putting work in, and there it's going to balance out your final potential energy over here. It doesn't matter which equation you use when we're problem solving. We just need to keep in mind that work is the force times the distance. Okay, work is force times the distance. Don't forget that equation. Work equals force times distance. Okay, and again, friction is what we'll be dealing with for the most part, and friction, it should be force of friction, is equal to mu times force normal. Remember, that force normal could be equal to weight when it's flat, level ground. If it's on a slope, then it's equal to the y component of your weight. Just a few review items. So next we'll tackle some example problems in the next video, and working with our workout equations. And again, sometimes maybe you like to use this equation, maybe you'll find that you like to use this equation. Whichever one you use, it doesn't matter. You're gonna come up with the same answer.